Okay, guys, so today is the big leagues. This is one of those lessons that it's going to have a lot of information in it. You may have to take breaks occasionally or rewind and re-listen to some stuff, but this is the heart of Algebra 2, in my opinion. This is one of those topics where when you leave Algebra 2, your teachers are going to say, this is what they know now that they've taken this class. And transformations is sort of the topic of the day. I think I already told a lot of you guys that there's a lot of what we call parent functions in Algebra 2, and these are just different types of graphs that are so important that the whole world studies them. And so you know what a linear function is. You've known that for a couple of years, and that would be just a line. And you even probably already know what a quadratic is, but we're going to use quadratics today for this part of the lesson. And then we're going to talk about two new parent functions that you may not know. So let's jump right in with the parent functions, these three parent functions. Now, quadratic is the equation y equals x squared. And on this graph, if you needed to graph it perfectly, you would just make an x and y chart over here, and you just start plugging in numbers, okay? And usually your teachers have you choose a couple of negatives, 0, and a couple of positives, and you make these up. We plug them in, and then we're going to get our answers over here, right? So -2 squared, so we've got 4, 1, 0, 1, 4. So I'm just plugging in and mathing it out real quick in my head, and then from there you get to just graph that information. And so once we go and graph that information, we've got a point here, we've got this, and then 2, 4 would be about there, 2, 4 would be about there. Okay, so for the parent functions, when I draw them right here, I'm being really careful about exactly where the points are, just because I want you to have good notes as to what they look like. But you know, this general shape is going to be the focus, because what this lesson is about is if I were to toy with this equation right here, you know, if I were to stick a number on the front or a number in the back or something like that, the idea is, would you be able to think about what that graph's going to look like in your head without having to do this X and Y t-chart? So do you understand what putting numbers on an equation does to said equation? And when you think of the graph in your head, you're never going to know exact points. You're just going to know, oh, okay, I think the graph's been maybe it's moved to the left, and maybe it's now facing downward, and maybe it's skinnier, and those types of things are transformations in what we're talking about, okay? But let's keep going through this now. Domain and range for this graph. For the domain, it's definitely all real numbers, and I'm going to write all real numbers as the capital R. You could also write X is between infinity and negative infinity. You could do like that. Either or is fine. For the range, it's all numbers greater than 0. You can probably see that 0 is the lowest number on the graph, and then it goes up. So you can choose to write that as maybe y is greater than or equal to 0. There's something called interval notation that you may or may not have seen before, and I'm going to put this is totally bonus over here, y'all. This is optional. You're not supposed to know this yet. But interval notation is a way of writing domain or range. It's not notion, sorry, it's notation, and I can't spell, so let's try that again. Notation. There we go. Yay. Okay, so with interval notation, what you're doing is it almost looks like a point, and you're putting on the left, like for range, you would put the lowest number that the graph can be, comma, the highest number that the graph can be, and then you put either a bracket or a parenthesis around your two numbers. Now you get to put a bracket on it if it's something you can land on. So kind of like this greater than or equal to. If you know you can land on it, you put a bracket. If you can't land on it because it's a concept, then you put a parenthesis. So this is interval notation. You'll see this year, but I doubt you know that yet. Okay, The next one is absolute value. Now, absolute value, you know what that does to a number, hopefully, because you've done that for the last couple of years, but it is actually a function as well. And so we're going to do the same thing. We're going to have our little grid here, and we're going to plug in numbers and see what this thing looks like. So this parent function, let's do the same ones we did a second ago. Just a few negatives, a few positives. Okay, remember absolute value. If you plug in a negative, what does it do? Well, it just makes it positive. Okay, when you plug in a negative, makes it positive. What if it's already positive? It stays positive. Okay, so these would be the points that go with this graph. And then what happens is when you actually graph that out, it looks pretty awesome actually. It looks like a straight line, but it's heading in two directions. Okay, so I'm just graphing these points right here and playing connect the dots. So it's not quite a parabola. There's no curvature to it. It is a straight line this way and a straight line up in the third quadrant, okay? And it forms almost a V. Some kids in your class will call it the V graph. And you could be like, that's absolute value, thank you very much. But anyways, that's the graph there. So what about domain and range on this? Okay, well if you look at it, I think the domain and range of this look pretty similar to that one, if not exact. It's still going to be all real numbers for domain. And for range, I'm going to do that interval notation that I told you about. It goes from 0 to positive infinity, okay? Now, what about the square root function? Okay, so a square root graph, the equation looks hopefully what you think it'll look like. It's the square root of x. Okay, so notice the names of these are basically exactly what the equation looks like. Okay, so with the square root graph, y equals the square root of x. We're going to do the same thing. We're going to do a couple of tallies here. La, 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 la. Okay. So when we go to do our chart, this one's a little like not as fun. We'll do a couple of negatives. We'll do a couple of positives. Okay. So how does this work? Well, if we plug a negative square root, or sorry, a negative 2 in underneath the square root, let's think about that. The square root of a negative number, that actually doesn't happen. That can't happen. It is an imaginary number. And so it's not something that we can graph. So I'm going to put NA because I can't graph anything that goes with that number. Same thing with negative 1 for the same reason. We can't graph anything because it's a negative underneath. Is there a square root of 0? Yes, there is. Is there a square root of 1? Yes, there is. Is there a square root of 2? There is, but we may not know it. Now, if you were to look at this on the calculator, the square root of 2 is actually 1.4-ish. So that's what I'll be graphing. All right, so now we're going to come over here and try to make this thing happen. So we've got 0, 0, 1, 1, and 2, go over 2 and go up 1.4. Now, if you notice, this thing almost looks like, whoa, what happened to it? Ah, there it is. This thing almost looks like it's going to form a dome or something, but I'm telling you, it's not going to come back down. And if you picked a few more numbers here, you would see it ain't going to come back down. It's going to continue to go up gradually, and it's going to look something like that, okay? This one I always think of as like the projectile graph is what some of my students would call it, because we could imagine like someone shooting like a bow and arrow type thing down here, and that's what it reminded me of. But that's what this graph always looks like. Domain and range. Okay, so let's look at domain. This one is going to have a different domain, guys, because there are no negatives allowed. So your domain starts at 0, and then it can be anything bigger than 0. So using interval notation that I explained over here, I would write it like this. If you want to write x is greater than or equal to 0, that is perfectly acceptable as well. And now for range, let's look at the graph. There's no negatives on this graph either. It's y values that are 0 or beyond. So same thing, it's going to be the same thing as domain, except we're using a y instead of an x. All right, cool. So now you have 3 new parent functions, and throughout the year, I think you're going to have a total of 8 or 9 this year, probably 8. So now you've got half your parent functions so far at our halfway point through summer, okay? Now what are we going to do with these? Well, the goal here is going to be you don't want to have to make a T-chart for every single equation that I give you. So what we're going to learn is what the significance of the numbers that you see based on where they're located in the equation. So as an example, let me kind of show you, what this is going to look like, okay? So there's a generic transformation form, and what I'm going to do, and we're not going to do every single transformation because that would be crazy. I'm just going to focus on a few that that you might run into in algebra, okay? So first you have to start with the parent function. Now for the parent function, I'm going to call that f of x, okay? Because, and I'm actually going to leave a little room to groove all over the place. F of x, this is going to be your parent, and the parent can change. It could be, you could be looking at an x squared right here. You could be looking at an absolute value. You could be looking at a square root. So I don't know what my equation is going to look like. There's just going to be some kind of parent, and then there's going to be numbers all around it. And like I said, those numbers are significant. So the first thing is you could have a negative in the front of everything. And if you have a negative in the front, okay, and I'm going to put negative in the front, what that does is an x-axis reflection. And some teachers are going to call that a vertical reflection, okay? So it'll take your picture and it's just going to flip it basically down. So if it was a parabola that goes up, it's now a parabola that goes down. The next thing that you could see on your x squared or square root of x or whatever you're looking at, you could see a number multiplied in the front, okay? Now a is just a number, okay? And this multiplier that's in the front does what we call a dilation, and it does a vertical dilation. So what this means, when you dilate something, you change its size. So this is the whole, does it become skinny or does it become wide? And the way that you can tell is if your number A is bigger than 1, so if it's a 2, 3, 4, 5, whatever, you're going to have a stretched out graph, which will make it appear thinner, okay? But if that A is a fraction, let's say it's a fraction between 0 and 1, like maybe it's a 1/2 or a 1/3 or a 3/4, if you have that, it's called a vertical shrink. And if you shrink a graph, it appears fatter. So feel free to add any notes to this that I'm not actually writing down. We'll do some examples and maybe that'll help clarify, okay? So those are different things that can happen to the front of your x squared. Now, if it's something that happens on the inside of the function, and like I said, this will make more sense later, then they do different things. For instance, if you have a b, these are the least fun, I'm not gonna lie. If you have a number that's a multiplier that's on the inside of your parentheses, then that b right there is a horizontal dilation. Horizontal. This doesn't happen very much. In fact, I don't even think I'm going to put it in your practice problems because this is really hard to wrap your head around. And horizontally, I should have put horizontally and vertically, sorry. Horizontally dilated. It's really difficult without doing a T-chart to see exactly what's happening. You're stretching and shrinking your graph, but you're doing so on the x-axis. And so it still makes it skinnier or fatter, but it's in a different way, and it's hard to do without a T-chart. I'm even going to write that. I'm going to recommend a T-chart on this where you do just make out your points until you understand what's happening. So you'll see that in school. You won't see that on this summer lesson. This is just an intro, okay? Now, what else can you see? Now, you're also going to see, you could see a plus or minus a C. Okay, so that's what I'm talking about with all these A, B, C, Ds. The C could be a number. So if you see a number added or subtracted to the inside, this is going to be a translation left or right. Translation. If you see a plus, it's going to move left. If you see a minus, it's going to move right. And that may be the opposite of how your brain thinks, and it is mine too, but that's what happens oftentimes when you're inside of parentheses. It does the opposite of what you want it to do, okay? And the very last thing that could be there is on the outside of the function, there could be a number added or subtracted to the outside of the parentheses or the outside of the parent function. And when that happens, you're doing a translation. But now it's the other direction. Instead of left and right, it's up and down. And this one does make sense. If it's positive, it goes up. If it's negative, it goes down. So what we're going to have to work on, this looks really weird, and you're like, I don't really get this yet, and that's okay. You will hopefully get it once we do an example with a real parent function. Just kind of keep this chart handy until we get good at it. So let me show you how it's going to apply to the three different things, okay? Now, if we have a quadratic, that has some stuff going on. So I'm going to say, like, what if you're given the equation y equals negative x plus 2 squared minus 4? Okay, so if somebody gives us this equation, your job is to compare this to the parent function. So since I see a parenthesis and something squared, the parent function is x squared, okay? That's how we wrote it above. So what has happened to the x squared? Well, there's this negative in the front, and we already wrote over here, if there's a negative in the front, I know that this is going to flip over the x-axis. The other thing that's been happening to the x squared is there's this plus 2 in parentheses. So if we look at a plus something in parentheses, that is like the C that I wrote here, which means it's going to go left or right. Now it's a plus 2, so that means it's going to go left 2. And then we have this minus 4 on the outside of the parenthesis, which is like the D from above. And the D says that it means you're going to translate it up or down. So if it's a minus 4, I know this is going to go down 4 units, okay? So you use this to sort of take your notes as to what numbers are in the equation and what's going to happen, and then all you have to do is be able to actually draw your function. So I always make my class start by drawing the actual parent function, which is x squared, and we drew that above. So take a minute to draw x squared. That was the 0.11, that was the 0.24. And I may need to make this a little bit steeper. Try to make yours a little better than mine. I'm pretty terrible at being accurate, and that's part of the curse of that's what makes me sometimes a horrible math person, is my stuff's not very precise when I go to graph it. Okay, so this is my parent. Try to make it match the grid of over 1, up 1, over 2, up 4, over 1, up 1, over 2, up 4. Okay, now we start doing this stuff to it. So I did some color coding, and if you can't color code, that's fine. Maybe just put like a number 1, number 2, and number 3, so that when you're graphing these, you can label them with 1, 2, 3. So the first thing I'm going to do is an x-axis flip. So I just reflect my graph down. That's pretty easy to do, right? Now the second thing is I'm going to shift this entire gray graph left by 2. So I like to use the vertex as my point, and I'm going to move that to the left 2, redraw the vertex, and then I need it to still be going down, and I still need to try to keep the same slope that I had here. So that was over 1, down 1. Over 1, down 1, over 2 down 4. So it's going to look something like this. Okay, so I'm trying my hardest to keep the same size. I don't want to stretch it any or shrink it any. So maybe use those points of over 1 down 1, over 2 down 4, and that'll help. And then the last thing is the blue says to shift this, now this green graph gets shifted down 4. So I'm going to take the vertex and now I'm going to go down 4. 1, 2, 3, 4. So now that vertex is down here. And I'm going to do the same thing. I need to go over 1, down 1, over 1, down 1, over 2, down 4, over 2, down 4. And that is going to be my final answer. Okay, the blue's my final answer. I like my class to show me every single step of the way. And then sometimes when they get really, really good at it, then I let them erase all the old graphs and just stick with the new one. Okay? All right, so we're going to do the same thing with these last two. Now, I know this is a long video. Remember, if you need to take a break, take a break. Or if you want to take a break right now and go to the practice problems and hunt down anything that has an x squared and try it, then feel free to do that, okay? We are going to try an absolute value graph next, okay? So with an absolute value graph, that is, you may see an equation like this. Okay, so we're just going to do something just like that, all right? So the trigger is I look at an equation and I see absolute value bars. And so these are really easy to identify because you're like, oh, duh, it's got absolute value, so it must be that V graph, okay? So you just need to identify what's changed from this equation to this equation using our generic transformation form. And as I look at this, the first number I see is a 1/2. Now that 1/2 is multiplied by this function, and it is on the outside of the parentheses. Now, the parentheses are the absolute value bars for a problem like this. So that means that it's the A. And if you read above, A is supposed to be a vertical dilation. And then you look at whether or not this is greater than 1 or less than 1. Now 1/2 is less than 1, so it's going to vertically shrink this graph. Okay, and that's just reading the notes that you have out to the side. So go back and read those right above. It's up here somewhere if you need to read them. Now, the x is an x. It matches what I see here, so I ignore that. But there is a +1 inside of the bars. So a +1 inside the bars is like a +1 inside the parentheses. So this is like the C. Okay, so the C is the thing that moves it right or left. And since it's a +1, it's going to go left 1. And now there are no other numbers. There's no negatives. There's no numbers back here. So that means that this graph is just taking my parent and only doing 2 different changes to it. So I'm going to start with my parent. Okay, my parent is the V graph, and it goes over 1, up 1, over 1, up 1, all the way across. Over 1, up 1. Over 1 up. So it looks something like that. So that's just my parent function, absolute value of x. Now I'm going to graph the vertical shrink. Okay, so the vertical shrink says that I'm supposed to, it's almost like I've got a board across the top and a board on the bottom, and I am pushing down on this board that's up here. So I'm trying to shrink the graph, so I'm pushing down on it, which means it's going to make this graph fatter. And if you're like, well, how much wider or fatter is it supposed to be? Well, there's an easy way to figure it out. You can just take the y values that you see here and multiply them by whatever's here. So if that number is 1/2, then I just take this y value of 1 and multiply by 1/2, and it's going to go here now. I take this y value of 2, and it's now going to be at 1, okay? And that shows you exactly how much fatter it's going to be. So over here, this y value is 1. It's now 1/2. This y value is 2. 2 times a half is 1. It's now here. So that gets pushed down by half the amount of space that you see, and now it's like a super wide V, okay? And now I finished my vertical shrink. So the only thing left is to take this bad boy and shift it to the left 1. So I'm going to start with my vertex, move it to the left 1, and then I'm going to try to keep that really wide thing going. So see, I tried to make those kind of parallel. That's kind of how I'm looking at it, is I'm trying to make those parallel, and when I do that, it's going to mean that I've kept the same width. Woo! All right, so that's how you handle a vertical dilation. It's almost just a multiplier by your y values. So if you want to write a little note down here, you can take the a in the equation and multiply by current y values. And that's going to give you the new y values, okay? All right, cool. And the last one, I know this is a long video. Gosh, I'm sorry. But there's a lot of information here. Okay, the last one is a radical. So a radical would be like, maybe I give you y is equal to negative square root of x minus 1 minus 1. Okay, something like that. So if you see this, then you see a square root in the equation. As soon as you see a square root in the equation, you should be thinking, oh, okay, well that is the square root graph. And so you could come over here and start by just graphing your square root function, which looks like this if you look above. Okay, it's something like that. Okay. Okay, so there's my square root graph that we did above, and this is our starting point, and now we just look, how does this equation differ from this equation? Well, there's a negative in the front. So what does a negative in the front tell you? Well, that tells me there's going to be an x-axis reflection. So I'm going to go ahead and do that first. So I'm going to take this whole graph, I'm going to flip it across the x-axis, which means now it still starts here, but now it goes down instead of up. Okay? The next thing I see is under the square root, there is a minus 1. Okay? Well, this square root almost acts like parentheses because you're trapping numbers inside of the function. And so just like here, these were like parentheses. Here, these were definitely parentheses. But here, these act like parentheses. So this minus 1 is it's the C. All right, so the C does right or left. Since that's a minus 1, it's going to be right 1. And then you've got this minus 1 on the outside of everybody, which means it's the up or the down. So it's down 1. So now I'm going to take my gray graph and let's do these other two transformations to it. So the gray one is already done, and now I need to take it to the right one. So I'm just going to shift this over right 1, and then this whole thing gets shifted so it looks kind of like that. It might be a little wider. There we go, something like that. And then now I need to take it down 1. So I take the green graph and I'm moving it down 1. And then I recopy that same green graph as best I can. So the blue graph is your final, okay? And you can make it bold or label it with final or number 3 or whatever you want to do. But that would be your answer. Okay, cool. So do your best on the homework. I tried to make them not too killer, but and I gave you grids, which makes it a lot easier. And then after you try as many as you can, of course, the solution video, I'll go a little bit quicker, but we'll see how you did. You can also check yourself with a graphing calculator if you don't care to watch the solution video, or if you're impatient and you just want to know immediately if you got it right. All right, see you guys.